Okay, so last time we defined the complex numbers, and there they are. There's their definition of a complex number. It's just two real numbers. It's real and its imaginary part. And then we defined the zero complex number. We defined one. We defined addition, negation, and multiplication. And then we added some simple lemmas, things like this. What can I do? I can do this. We added some simple lemmas like this. It says the real part of z times w is what it is. The point, even though this is true by definition, we told the simplifier about this by giving this lemma a name and tagging it with the simp attribute. And by the time we'd done that for lots of lemmas, we realized that we were one step away from proving ring complexes are a commutative ring very, very quickly. This extensionality lemma here. This extensionality lemma says that if two complex numbers have got the same real and imaginary part, then they're equal. And we tagged that with ext. And so the ext tactic knows about this extensionality lemma. Two complex numbers are equal if they're made from the same things, i.e. made from the same real number and real part and imaginary part. And so then the proof that the complexes were a ring looked like this. We introduce our variables. Let's see something in action there. We introduce our variables, and this is the kind of thing we've got to prove for the complex numbers. And then by extensionality, we've got to prove analogous statements for the real and imaginary parts. And then the simplifier breaks this down into a statement that's 100% about real numbers. And then the ring tactic solves that because the real numbers are already a ring. So that was what we did last time. And let me just briefly go through some extra stuff that's at the bottom of this that I didn't live stream last time. But here's some chat about how you can rewrite stuff in term mode. I won't go through this. But I will just remark that there are two other lemmas I proved. The first one is that I could write that more nicely. What does this say? This one says if z is a complex number, then the complex number you make, there it says this. If I've got a complex number, then I can get two real numbers, its real part and its imaginary part. Well, I write it in a way that mathematicians can understand it. There. If I've got a complex number, then I can take its real part and imaginary part, and I can make a new complex number with real part, the real part, and imaginary part, the imaginary part. And unsurprisingly, this is equal to z, although that turns out in Lean not to be true by definition. And we just have to, what do we have to do? Oh, it's true by definition once we break z into its real part and imaginary part. So there's a proof by induction or something. And then finally, there's this lemma here, which we did prove last time, basically, the extensionality lemma. The hard part we proved last time. If two complex numbers have got the same real part and imaginary part, then they're equal. But the converse is that if two complex numbers are equal, they have the same real and imaginary part. This is an if and only if. And this if and only if version, X was an implication, X if is an if and only if. It says two complex numbers are equal if and only if they have the same real and imaginary part. And the proof is relatively simple. I won't go through it now. And there you go. There's an incredibly small proof of that in term mode. So that was where we ended up last time. And today I'm going to start here talking about the map from the reals to the complexes. So I rearranged things. I thought we were going to do the square root of -1, but the square root of -1 is too difficult for us yet. So I'm genuinely concerned on my, am I just being an idiot? On my screen, no, I'm just way behind. I'm just going to have to deal with it. So here's level 1, and level 1 is now the map from the reals to the complexes. So what's the definition of the map from the reals to the complexes? We start off with a real number r, and we have to make a complex number, and clearly we're going to make this complex number here, r, 0, right? The complex number with real part r and imaginary part 0. So So let's make that definition now. Here is the definition. So of real is the map from the reals to the complexes. And it's going to send a real number r to the following complex number. We'll have, well, I can make it like this. Its real part can be r, and the imaginary part can be 0. There we go. So there's the canonical map from the reals to the complexes. And so now we've got this map. Now we have to prove lots of things about it. In fact, we have to prove 12 things about it. I can see because there's 12 warnings. And the first thing I'm going to do, in fact, before I prove anything about it, is I'm going to, this map here, you see, this is currently a visible map, right? I wrote some blog posts a couple of weeks ago about invisible maps. So currently, you see, we can have an example. We can make a complex number like this. We could do of real, 37, because 37 is a real number. And so I've just made the complex number 37. But what I really want to do, here's an example. Let's say r is a real number, and I want to make a complex number, and I want to define that complex number to be r. And it doesn't work, right? Because I have this type mismatch error up here, because r is a real number, and Lean was expecting a complex number. So I want to make this map invisible, right? So currently it's visible, because I can write of real r. There we are. And now we can see that, yeah, so now this is compiling. You see there's no errors down here. If I remove of real, then down here at the bottom I have some error. So let's put that map back. So currently this map is visible, but after this line here, where I set the map from the, I define of real to be the coercion from the reals to the complexes, and now I can move this down here, and so now I can get rid of this. There. Now the map's become completely invisible, you see. And actually, if we, how can we do this? Here's what we could do. We could define a function from R to C to be the function that takes a real number and it goes to R. And if I look at F, there, you see there's this funny little up arrow here. There's this little up arrow here, and that up arrow is the invisible map. These up arrows are just maps, which Lean isn't going to even bother telling you the name of the map, but the idea is that map is there. So, R is strictly speaking a real number, but we're regarding it as a complex number via some coercion. So there's my coercion. And now we need to prove a whole bunch of really trivial things about this map from the reals to the complexes, and of course they're all going to be very easy. So here's the first one. What does it say? This first one here says if I take a real number and then I imagine that it's a complex number and I take its real part, I get R again. And I think that's going to be true by definition, right? REFL. Yeah. So that's true by definition. The real part, you can see that because R colon complex, that really is just shorthand. What is the goal really? Goal is really the real part of this thing here, R0, is R. But the definition of the real is that the real part of whatever, xy, is defined, is defined to be y. Is defined to be x. So that's why this is true by definition. And similarly, this one here, the imaginary part of a real, take a real number. So this function, what does this function do? Of real im, it takes a real number, and then the theorem it's proving, this is a theorem. The theorem takes a real number as input, and it outputs a proof that its imaginary part is 0. And because this complex number here is by definition the complex number with real part r and imaginary part 0, this will also be true by definition. So there we go. There's the tactic. There's the term mode version of it's true by definition. So the map from the reals to the complexes is injective. So right. So now we have to do. Oh, before we start on this, I should tell you something else. I'm tagging these lemmas with simp because we want to get the simplifier to prove things about this map for us. But I'm also tagging them with something else. I'm tagging them with normcast. So what does the normcast tactic does? We want this map to be truly invisible, right? A mathematician thinks of the reals as a subset of the complexes. I mean, and this may or may not be actually true, but whether or not it's actually true, we certainly want to pretend that it's true. And so the idea about norm cast is that you're trying to prove some equality about the real numbers and you accidentally prove some equality about the corresponding complex numbers. Then we want it to be completely invisible. We want to be able to deduce the fact that it's true for the real numbers, in a completely transparent manner. And we have a tactic for doing that, the norm cast tactic. So here we're training the simp tactic and we're training the norm cast tactic. I'll show you the norm cast tactic in action in a minute. So how are we going to prove this? What does this say? Of real ing, this says we've got two real numbers r and s, and the claim is that the corresponding complex numbers are equal if and only if the real numbers are equal. So I guess I could, well here, this up arrow r equals up arrow s, that is a statement about equality of two complex numbers. So I suppose I could rewrite xdiff there. And now you see the goal says, yeah, you see now we could simplify this, couldn't we? Let's try simplifying it. Yeah, there you go. So the proof is finished, right? So what happened there? We started off, we had to prove that we've got two real numbers r and s, and we wanted to prove that the corresponding complex numbers were equal if and only if the real numbers were equal. And what does it mean for these two complex numbers to be equal? It means, by definition, it means that their real parts are equal and their imaginary parts are equal. There. So this is a useless thing. This is obviously true because this just says 0 equals 0. And this, when you simplify it, it says r equals s. So the simplifier, we can even have a look. If we type squeeze simp here, there, we can see what the simplifier used. So what did the simplifier use? The simplifier used these things we've just proved. It used of real im and of real re. You see, if we hadn't tagged these with, if I removed the simp tags from this, and this, then it might break. Yeah, you see, this proof now breaks, you see. The simplifier can't simplify this anymore. So as we're going on, proving more and more lemmas, the simplifier is slowly getting cleverer and cleverer. You see, this is the reason why we have to prove these things in the right order. So let's tell the simplifier about that again. There. Now the simplifier knows about these things. And we're back. You can see what it used. It used of real im, it used of real re. And these things here, and true. I think and true is the lemma that x and true is equal to x and true is equivalent to x or something. So we use some sort of trivial logic lemmas. I wonder if actually I could maybe do this. Simp xdiff, will that work? There. So that's actually a very, there's a very short proof. This tactic proof is one tactic long now, and so I can use by. By is the same as begin end. If your tactic proof turns out to be so cool that it's only one tactic long, then instead of begin end, you can just put by. So that's this. Oh, so now we've trained normcast. We've trained normcast in the art of real and imaginary parts. This is the key thing. We prove that two real numbers are equal if and only if their real parts and imaginary parts are equal. So here's the kind of thing. There, let's have a look at these proofs. So here we're in the situation, we've got a hypothesis where we know we've got two real numbers r and s, and we happen to have proved that the corresponding complex numbers are equal, and we want to prove that the real numbers are equal. And I don't want to start using the simplifier and blah, blah, blah. I want to use, this is obvious, right? This is so obvious I shouldn't even need the simplifier, because Lean should somehow know that two real numbers are equal if and only if the corresponding complex numbers are equal. And the normcast tactic does this. The normcast takes somewhere, normcast takes a statement where there's arrows in the goals and it removes them. So what's this proof here? Normcast at h. You see it just turns there. H used to have arrows in, but when you use the normcast tactic on it, the arrows go away. And so now this is really easy to prove because our goal is exactly h. And similarly here, we've got two real numbers r and s, and let's say we've managed to prove that the real numbers r and s are equal, and we want to deduce that the complex numbers r and s are equal. We could do that with some rewrite probably. Maybe we could do sort of rewrite h or something. Yeah, that would do it. But there's this algorithm that will do it for us. We apply the normcast tactic. You see, there used to be arrows in the goal. These are invisible maps, but the normcast tactic just removes the arrows. So again, this is easy because the goal is exactly a hypothesis. So that's the point. That's the point of normcast. So now what's happened here? We've made a new definition, right? Everything was a theorem apart from this very top thing here. We have one definition, and that definition we now have to explain about how that definition plays with all the other definitions that we've made thus far. So what definitions have we made thus far? Well, 0 is something that we've done before. So we need to prove what's the lemma about real numbers and 0. The lemma is going to be that if you take the real, this says take the 0, which is a real number, and then regard it as a complex number, right? So this says this is 0 as a real number, but then this colon says regard it as a complex number is 0. And you can look at the goal. So you see we've got an up arrow on one side, not the other. So it looks like it should be true by REFL. Let's try REFL actually. Yeah, REFL does work. So there you go. Why is that? I see it's because both sides are by definition the complex number with real part 0 and imaginary part 0. So that's true by definition. This won't be true by definition. Who knows? Let's have a look at this proof. Of real x0, we've got a real number z. Oh, we should call it r. That's a terrible name. There. Note to self. Note to self. Change z to r. There you go. That won't break any of the proofs because I just changing a variable name is changing everything up to alpha equivalence. So what's happening now? Oh, my fan is going crazy. That's one thing that's happening. This says we've got a real number r, and the claim is that the real number r. Yeah, do you know? Will the simplifier do this? The simplifier won't do it. Well, let's try xdiff. Let's tell the simplifier that it can use xdiff. There you go. Great. So this is mathematically trivial, but the simplifier is now smart enough to do this kind of job. As long as it knows about xdiff. You see, there's one thing the simplifier doesn't know. What does the simplifier? Let me show you something. Let me teach the simplifier attribute simp xdiff. If I tell the simplifier about xdiff, remember xdiff says this, right? Xdiff says two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. If I tell the simplifier about that, then probably the simplifier will be able to do this. Yeah, the simplifier's done it, right? There's no errors. Maybe I should make this local. I'll make this a local attribute. So the simplifier knows just for this file. For this file only, the simplifier knows about xdiff. So it's slightly problematic telling the simplifier about xdiff, because now that whenever the simplifier is faced with the goal of proving that two complex numbers are equal throughout all of mathlib, if I tagged xdiff with simp, then throughout all of mathlib, whenever you tried the simplifier on a goal involving complex numbers, it would somehow try and break them up into real and imaginary parts. And that's not what you always want. But it is what we want for these simple things here. So now let's try this. I think the simplifier should just prove this automatically. Yeah, you see the simplifier's got quite smart now. Of real ne 0. So now what about this? So that's the end of 0. What have we got? Let's think about what we have. What should we be doing now? What things have we defined already? We've defined 0, 1, addition, negation, and multiplication. So we should try and work out how they interact with this invisible map of real and prove the corresponding lemmas and tag them all with simp, you see, because we want the simplifier to get more and more powerful as things go on. You know, we want the simplifier to prove more and more lemmas, because ultimately, you know, when you're actually in the wild using complex numbers, sometimes you'll want to do things about relating the sum of two real numbers to the sum of two corresponding complex numbers, and you want the simplifier to be able to just deal with these things immediately. So of real 1, is that true by, this might be true by definition, right? Yeah, this is true by definition. Because the left-hand side is by definition the complex number with real part 1 and imaginary part 0, and the right-hand side is just the same. So that appears to be the only lemma I'm proving about 1. So what about addition? So there you go. So this says that this map of real is an additive group homomorphism. You see what the goal says here. You take two real numbers, R and S, and then you add them up, and you get a real number, and then you consider that real number as a complex number. The answer, sorry, when I add two, I'm just looking at the chat. I add two real numbers and then consider the result as a complex number, and the claim is that we get the same answer as taking each real number, assuming they're complex numbers, and then adding them up. And so you would imagine that this would also be true by definition, right? So think about, you try and do this exercise in your head. So, so do you understand mathematics, right? Is this true by definition? And we can try it. Let's try it. Refl. And yeah, I knew that was going to fail because I can see that it's not quite true by definition, but it looks really true by definition. So just out of interest, let's take this apart. So let's apply extensionality. So now we've got two goals, and the first goal is that the real parts are equal, and the second goal is that the imaginary parts are equal. So let's do refl here. Let's do refl here. So let's try and so the claim is that both the real parts and the imaginary parts are equal by definition, and it's true for the real parts. The real part of this is by definition R plus S, and the real part of this is also by definition R plus S. But the imaginary part, it's sort of funny because this is a lemma about real numbers, but the imaginary parts, why are the imaginary parts not, why is this not true by, this just says 0 equals 0, right? So what's going on? Let's take apart what this says, because we can see the invisible map, and yeah, we can see all the maps involved. And now let's just unfold them. Let's rewrite. What can we do? We can rewrite of real in there. So that's unfolded something, and we can rewrite rewrite add in there, and then we can rewrite of real in again. And we'll probably have to do that twice. There we go. And now we can see what the goal is. And you see it's not true by definition. because 0 plus 0 is a really, what are the real numbers? They're kind of, equivalence classes of Cauchy sequences. And 0 plus 0 is some kind of complicated, it's just a complicated thing defined by some sort of, defined by some universal property of equivalence relations. So this is certainly true, and it's true by, it's certainly true, but it's not true by definition. That's the point. So I guess my guess is that the simplifier knows that x add 0 is x. So if I type simp, yeah, you see the simplifier has done it there. So you can see all of these things. These are all, this of real im is true by definition, right? You look at the proof of real im. Where's the proof? Where's of real im? Here, of real im here is true by definition. There, and similarly add im. If we look at the proof of add im, we can do that if you like. I'm slightly surprised that looks like that. Anyway, if we look, we can peek the proof of add im there. And what was the proof of add im? Im z plus w is im z plus im w. That was also true by definition. So all of these things were true by definition, but that last part. So what does the simplifier use? So if we look at squeeze simp there. So add 0 is the lemma it used. So in fact, probably here we might be able to put exact add 0. Add 0, 0. Oh, we can't do that. Oh, it's the other way. What have I just done? Let me go back. 0 equals 0 plus 0. So it's exact add 0, 0, add 0, the real number 0. But it's not that. It is this, but the other way around. Oops. There. So now you can see, so now we can get rid of all of these if you like. There. So there's the proof. The real parts are equal by definition because they're both r plus s. But the imaginary parts are not equal by definition. They're equal because 0 equals 0 plus 0. But you see, it's nicer to do it with the simplifier, right? So, I mean, this would be a way of, if I wanted to write this in term mode completely, then I could maybe use this add 0 thing. But my instinct is to use the simplifier because it just looks nicer. And also because we added, yeah, the simplifier knows about xdiff, so probably the entire thing can be done by simp. There we go. Right, so similar question. Do you think this is true by definition, right? Is it true that if I take a real, what am I doing? Take a real number and then take its, yeah, take a real number. Is it true that minus the real number, regarded as a complex number, equals take the real number and then regard it as a complex number and then take minus of it? So, yeah, I could have applied it. So, I guess, why is that not true? Oh, I see, that's not true by definition because the imaginary part of this is 0 and the imaginary part of this is negative 0. So I guess the simplifier will know that negative 0 is 0, which it does. There. So now is this true by definition? So it's extremely unlikely to be true by definition. It isn't. But can the simplifier do it? Oh, the simplifier can do it. Oh, good for the simplifier. That's kind of, I'm slightly surprised the simplifier can do that. Just out of interest, I'm going to look at what happened there. Was that true by definition? Was that true by definition? Oh, I see. The first error is here. Oh, we don't know about the imaginary part yet. So why was this not? So let's do. Yeah, let's just unravel this, just out of interest. This is the last one I'm going to unravel. So let's rewrite of real re, and then let's rewrite of real mul. No, mul re, and then let's rewrite of real im, and then let's do that again. I see, and we need to rewrite of real re as well. Oops. Let's change these to re. And you can see, so there we go. So this is when you actually unravel what's going on. The reason it's not true by definition is because the left-hand side is r times s and the right-hand side is r times s minus 0 times 0. But then if you run the simplifier on this, I see. And then we could put squeeze simp here to see what the simplifier actually used. And indeed it used, yeah, it used mul 0, which is the same as the x times 0 is 0. So that changes 0 times 0 to 0. And then it used sub 0. And sub 0 is the theorem that x minus 0 is x. And that's not true by definition, but the simplifier knows about it. In fact, I could have done everything like this, couldn't I? So the imaginary part will be just the same. I could do squeeze simp there, and then we can see these are all the facts that the simplifier needed to prove that the product of the real numbers r and s, regarded as a complex number, is the product regarded as a real number. Yeah. So mul im xdiff mul re mul 0. There you go. Mul 0. Oh, and sub 0 as well. Ah, so in fact the imaginary part. Did we also need to add 0? I'm surprised add 0 isn't there. I have no idea why it isn't. What? Oh, add 0 is there. That's why. So there we go. So now let's prove that the canonical map from the real to the complexes is a ring homomorphism, but we've done that already, right? So what's this? This is a definition of real. You see, ring homomorphisms are not equal to functions, right? There's some kind of invisible map here. There's some invisible map going. What's going on? A ring homomorphism is a function and some proofs, but in Lean, a ring homomorphism is all bundled together to be one object. So it's not the function and then the proofs go somewhere else. A ring homomorphism is one object which contains as its parts the function and all the proofs. So this is a definition because it contains data. The data is the function. So there's the data. And now we have to prove, you see, what do we have to prove? How do you prove that a map is a ring homomorphism? You can see what's going on. If I put begin, end here. There. What do we have to prove about this ring homomorphism? We have to prove, what do we have to prove about this function to prove that it's a ring homomorphism? We have to prove it sends 0 to 0. This one here, we have to prove it sends 1 to 1. This one here, we have to prove it commutes with addition. Here we have to prove it commutes with multiplication. And these are exactly the things we've just been doing. So now we can define the ring homomorphism from the reals to the complexes, and there's the proof that it's a ring homomorphism. So here's the very last bit. This is what's going on here. So what is bit 0? Bit 0, let me show you what bit 0 is. Look at this. If I check the complex number 37, then it just says it's 37. But there's some clever notation going on here. There's some numeral notation. And if I switch the numeral notation off, and then we look and see what 37, this is what Lean really thinks that 37 is. So 37 is being stored in binary here, right? So Lean starts off with the complex number 1, and then it says bit 0, bit 0, bit 1, bit 0, and bit 1. So what do these things mean? And I'll tell you what they mean. Bit 0 of x is just defined. We can peek the definition, right? Bit 0 of x, there. Bit 0 of a is defined to be a plus a, and bit 1 of a, it could have been 2 times a, but it decided not to use multiplication, we used addition. And bit 1 of a is defined to be bit 0 of a plus 1. So bit 0 just doubles the number, and bit 1 doubles it and adds 1. So you can see that's how you make, that's how you make binary expansion, right? Here's my 37. So I start with 1, and then I do bit 0 of it. So the binary number is now 1, 0. And now I do bit 0 again, so I get 1, 0, 0. And now bit 1, so I double it and add 1, I get 1, 0, 0, 1. And then I get 1, 0, 0, 1. So this is the binary representation of 37 written backwards. So 37 in binary must be 1, 0, 0, 1, 0, 1. And that's how these numerals are internally stored. And because we want to make sure that the real number 37 is obviously equal to the complex number 37, we're going to have to prove that bit 0 commutes. Bit 0 commutes with this, this map from the reals to the complexes. So this is just going to be simp bit 0, right? There. I don't think the simplifier. I don't think simp by itself will work. No, but simp bit 0. Bit 0 spelt correctly will work. And similarly here, the fact that bit 1 commutes with the map from the reals to the complexes will just be simp bit 1, I imagine. There, you can see, I suspect, I wonder if I remove the simp here on that break. Yeah, you see the proof. You see all the way, the simplifier is constantly learning. So simp bit 1 doesn't work now. Because the simplifier doesn't know how to deal, here's some complicated question about bit 0. Because I didn't tell the simplifier about bit. It's important you have to do, because bit 1 is defined in terms of bit 0, you have to train the simplifier in bit 0 first, and now everything's worked again. So now we have no errors, great. So that's level 1 done, and now let me just show you the kind of thing we can now do. This is the kind of thing, in 2018, I did a bunch of projects with undergraduates, and we were doing a bunch of number theory, and it was really annoying because we were constantly switching from the naturals to the integers. And it was just the same thing. There's an invisible map from the naturals to the integers. And even though it was trained to do all the right things, we didn't have the normcast tactic. So here's an example of a goal. We've got three real numbers A, B, and C, and we multiply A and B together as real numbers. Then we regard that as a complex number. And then we multiply it by the complex number C. That's just the same as if we were regarding them all as complex numbers. So you see the normcast tactic just does that immediately. Whenever you see a goal that has arrows in, the proof here should just be cancel the arrows, and indeed it's normcast. And here's another random goal here. We've just got A plus B times C, except the moment when you stop thinking about A as a real number and start thinking of it as a complex number occurs at different times on both sides. So these are obviously both equal, right? Because up arrow A means the complex number A, and without the up arrow it means the real number A, but we as mathematicians regard those two things as the same. In Lean, strictly speaking, they're not the same in Lean, because there's this invisible map from the reals to the complexes. But this thing here, mathematicians would really want to say this is obviously true by definition, but it's not true by definition, right? Look, it's not true by definition, but this tactic here solves it for you anyway. And similarly here, if I remove this commented out thing here, this says that the complex number 37 equals the real number 37. And again, that's not true by definition, because the definition of the complex number 37 is bit 0, bit 1, bit 0, whatever it was. But this normcast tactic does this for us. So we've trained normcast to play well with this map from the reals to the complexes. I have one funny thing going on there. What's that red? Oh, I see. That's nothing. That's because I've deleted something. I can fix that by putting this back. So I see everything on that left is git. That's nothing. What's this thing on the right? That's just a check. Right, lovely. So that's done. That level is done. And now if I go to level 2 here, and if I change, so finally, how many lines have we got so far? So there's 200 lines of level 1, and there's 350 lines of levels. So we've done 500 lines of complex numbers, and we still haven't defined the square root of -1, which I think is quite funny. So here's the square root of -1, and it's level 2, and I'm going to change this import. What was I just editing then? Oh wow, yeah, okay. I'm not going to change the import. The import works fine. I'm editing the I'm editing the source code. I shouldn't really be doing that, but never mind. So there's no errors now in this import, and now finally we're going to do the square root of -1. So let's define the square root of -1, and that's going to be the complex number. So this is a very short level, by the way. The complex number square root of -1 is defined to be the complex number whose real part is 0 and whose imaginary part is 1. There we go. And so now you can see here we've got how many? We've got 6 errors. No, 6 warnings. So now we have to prove 6 things. So here we are. Let's train the simplifier about real and imaginary parts of I, the square root of -1. Why is the real part of I 0? That's true by definition. Why is the imaginary part of I 0? That's true by definition. And why is I times I equal to -1? I think that won't be true by definition. And I think that the simplifier won't do it either. The simplifier won't do it because the simplifier has forgotten about xdiff. So I could do it like this. xsimp, this would do it. There. So that works. The simplifier only knew about xdiff in that previous file, because where was it? Where did I tell it about xdiff? There, I made it a local attribute, so it doesn't, even though I'm importing this file, xdiff doesn't keep its simp tag. So there's the proof of this, and similarly these proofs here. So what do we want? This is the key thing we really want to prove about I. If I have 2 real numbers, A and B, then the complex number with real part A and imaginary part B is A plus B times I. And if you look at the goal, you see I'm regarding A and B as complex numbers, and this addition here, this is addition of complex numbers. It has to be, right? This can't be addition of real numbers because B times I isn't a real number in general. So again, xsimp should do this. It does. And similarly, I can prove that any real number, we can make that real number by taking its real part and adding, as considered as a real number and then as a complex number, and then multiply out by I times its imaginary part. So that will also be true by xsimp. There, so that's the end of level 2. Now let's move on to level 3. And level 3 is this. What's level 3? Level 3 is complex conjugation. Right, so how long have I got? I've got about 15 minutes because I don't want to stream for more than an hour, really. So what's the definition of the complex conjugate of a real number? The definition of a complex conjugate of a real number is going to be, it's going to be the real part. The real part will be the real part, and the imaginary part will be minus the imaginary part. So how about that? There. So there's the definition of the complex conjugate of a complex number. Its real part is re z, its imaginary part is minus mz. And so now we have to train the simplifier to play, to be an expert at complex conjugation. And the first thing we should do, you see, we've got all these other definitions. What have we got, right? We've got 0, 1, I, real part. Right at the very basic level, when we define the complex numbers, we define these two functions, re and im. So those are the first things we should train on everything in order, really, right? So why is this going to be true? This is probably true by definition. It is. And this is true by definition. And now conj 0, this might be true. I bet this isn't true by definition. No, because minus 0 is not equal to 0 by definition. So this should be by x simp. There, and this will be by x simp. There. So we're training it now with respect to 0, 1, and I by x simp. So all these proofs are check on real and imaginary parts, and now it's easy by x simp. I forgot the by. So that's done this. And now similarly here, the conjugate of z plus w. Oh, so maybe this is an interesting one by x simp. Yeah, this one fails. You see, we have an error. So that's kind of interesting. So why? So the simplifier has nearly done it, but we can look at this goal here. So it doesn't work, right? And we can look and see why it doesn't work. And the reason it doesn't work is what's happened here. Let's think about. I mean, we could maybe I'll just show you. Look, begin end. So what's going on here? We could certainly apply extensionality. And now here, let's apply the simplifier. And here, let's apply the simplifier. There, so its imaginary parts don't work. So we apply the extensionality lemma. So to prove that the conjugate of z plus w is the conjugate of z plus the conjugate of w, we need to check that their real parts and imaginary parts are the same. And checking their real parts are the same are fine. But checking their imaginary parts is slightly too much for the simplifier. And let's try and work out why that is. So we could rewrite, what can we do? We could write conjim, I guess. There, and we could do it again. Oops. Let's not do it like that. There, oh, we can't do it again. Oh, we have to rewrite add in, don't we? There, and now what do we need to do? Now I think we need to rewrite add im again. There, and now we need to rewrite conjim. Oops. And twice. And there we go. So now we can see what the goal is. So here's the problem. The problem is to prove that negation. So remember, these are real numbers. The issue is to prove that negation commutes with addition. Why is negative a add b equal to negative a add negative b? And the simplifier happens not to know that. It gets as far. I see. The simplifier knows that negative open brackets a plus b is negative b plus negative a, which is kind of interesting. And so we've got to prove that negative b plus negative a is equal to negative a plus negative b. So we need commutativity. We need commutativity of addition on the reals. So there it is. So in fact, the way we could prove, I guess that we could prove this. So that was what was missing. And you can see that. I should have shown. So commutativity of addition was what was missing. And if we do this by x simp, we didn't have to do all that unraveling. Lean told us already. There. This tactic fails, and you can see why it fails. And it's exactly for this reason. Minus the imaginary part of w plus minus the imaginary part of z equals minus the imaginary part of z plus minus the imaginary part of w. So you can see what's needed. So we should tell the simplifier add com. So you sort of might be wondering, you know, why does the simplifier not know add com, right? Because that seems like a pretty simple thing. Maybe we should teach the simplifier, but we can't. So chat, if something's true by definition, does the simplifier already know it? The answer is no, and that's exactly why we were doing this stuff here. Let me comment out conj. Then yeah, you see things broke. So answer to the question in the chat, the simplifier doesn't know it, and you can see there that's true by definition. So maybe we could do this. Yeah, you see there. Let's just end the file here because we have a bunch of errors there. So now Lean is ignoring everything below. Lean is ignoring everything below here, and what's going on is that I've commented out conj. Conj is true by definition, but the simplifier didn't know it. And if you remove this, then you can see that what's missing is precisely the statement that the real part of the complex conjugate of 0 is 0. And so we have to tell this to the simplifier there. And if we don't tell this to the simplifier, then the simplifier gets stuck, but we can get the simplifier going again, saying, now all the goals that you know now, why don't you check they're true by definition? So there you go, that's the answer to that question. Now I'll remove this. I'll teach the simplifier this. Why is there an error up here? Oh, did I not? I thought I proved all of these things. What did I failed to prove. I failed to do this level. What have I not done? Complex INE0, where's that? Oh, I skipped something. Oh, sorry, I failed to complete level 2. The simplifier. Oh, the simplifier can't do it. Oh, that's a blow. Oh, okay, sorry, forget complex conjugation for a minute. We've got a problem here. We have to prove that I isn't 0. So let's intro. Oh, what's the definition of I isn't 0? The definition of I isn't 0 in Lean is I equals 0 implies false. So we can intro H, and H is now the same with that I equals 0, and we have to prove a contradiction. And my guess is that the simplifier can do that. Simp star at star. Oh, it can't. Because I see, because it doesn't know xdiff. Oh, okay. So there we go. Attribute. Oh, what a pain. Let's just rewrite it. Rewrite xdiff at H. Oh, that's a 3-line proof. What about this? Local attributes. Let's just teach the simplifier. Local attribute simp xdiff. There. And now the simplifier will be able to do that level as well. Okay, great. So now level 2 really is solved. Sorry about that. And now we're back on level 3. And what are we doing? There we go. Oh, so that's right. Why doesn't the simplifier know about add com? That was what I was distracted by. Why doesn't the simplifier know about add com? Because if you told the simplifier about add com, then it would start looping. If it had some goal that mentioned A add B, it'd say, oh, I know add com. Let's replace it with B add A. And then we think, oh, I know add com again. Let's replace it with A add B. And it might get stuck in an infinite loop. One thing about levels, things you teach the simplifier, is as a mathematician, we think of equalities as, you know, x equals y is the same as y equals x in mathematics. But to the simplifier, that's not true. You teach things to the simplifier, the left-hand side has to be more complicated than the right-hand side. This is the idea of all of these simp lemmas. Re-I equals 0. You see the left-hand side is more complicated than the right-hand side. I suspect if I do this, if I change this simp lemma, you see there now things have started breaking. Lean now can't prove that I squared is -1 because I've taught the simplifier the wrong thing, right? Even though that's true by definition, now when it sees 0, it will now replace it by re-I, right? It goes the wrong way. The simplifier needs to be told that the complicated thing equals the simple thing. Kind of a quirky thing. So all of these simp lemmas are very carefully written the right way around. So back to complex conjugation. Right, let's go. So this is by x simp. Why don't I? It seems like a good idea. Let's local attribute. I don't know if it's a good idea or not. Let's stick with this. Scott Morrison didn't seem to think it was a good idea. By x simp. So let's go with what he said. Oh, that hasn't worked. This is interesting. Conj mull, it doesn't work because this thing here, this is going to be true, but this is too complicated for the simplifier. So we should maybe, this is true because it's true in any ring and the real numbers are a ring, but the simplifier doesn't know enough ring theory to prove this. So let's do xsimp ring. There, now that's true. And now what's going on by whatever, by xsimp ring, well, maybe by xsimp. Yep. Oh, this is an implication. So the simplifier won't be able to do this one. The simplifier only proves equalities. The simplifier doesn't prove implications. I've got to prove that if z is equal to its own complex conjugate, then it has no imaginary part. So let's do intro h. Great, we have something to do. Intro h. Let's solve this level. The conjugate of z is z. So why don't I rewrite xdiff? Oh, why don't I simplify simp xdiff at h, and let's see what we actually get. So let's simplify. What does h mean? This is interesting. If the conjugate of z equals z, the simplifier can simplify that as far as this. The imaginary part of z is negative the imaginary part of z. So there you go. This is why the simplifier couldn't do it, I guess. We've got a real number r, and we know that minus r equals r. We have to deduce that r equals 0. So we need quite a high-powered tactic for that. My guess is that the linearith tactic might do that. There we go. So that's the proof of that. And now why is that there? That's because it's going to help for the next lemma. Right. A complex number is its own conjugate if and only if there exists a real number such that it's that real number. My guess is we need to split this. And so now we've got two goals there, and I'll put them into two different square brackets here. So now what's going on here? Z conjugate is Z. If the conjugate of Z is Z, then there's a real number such that Z is that real number. So intro H. And I guess I can, we've got to prove that there exists a real number such that Z is that real number. So I suppose I will use, what real number can it be? I guess it's going to be the real part of Z, because that's a real number. And now we've got to prove, now I bet this won't work. Now I'd like to finish this because I'm bored of this proof. But the problem is, I think I might need to know, I'm going to need to know this, right? Let's add this to the, have H2. Let's have this, H, there. So this lemma that we've just proved, we know that the imaginary part of Z is 0. And now I'm hoping that this will work. Ext, simp star at star. Will that do it? Yeah, that's done it. And so now what's the other way? Oh, hang on, there's a comma missing. What's going on the other way? So if I intro H, so now this says I've got a real, what does this say? So my hypothesis is that there's a real number such that Z is the conjugate, such that Z is the complex number equal to that real number. So I can do better than intro, can't I? I can do rintro RHR there. So now I've got a real number and the assertion that Z is equal to that real number, and I need to prove this. And now I wonder whether I can do simp xdiff comma star at star. I can. So there you go, the joys of automation. You just need to know exactly what you need. There. How are we doing now? What have we got left? We've got 7 left. Oh. Simp xdiff. Oh, curses. Oh! That might be true by linearith. Ah. These levels are trickier than I thought. What's going on here? So why don't we do simp first? what's actually happening. Can't simplify, okay. Let's try this. Let's tell us about its extensionality. And now let's do split, and now linearith on this. Okay, let's do split. I see split intros linearith. Right, that's done. So there we go. And now, why is the complex conjugate? No, Z add its conjugate is twice its real part. I wonder if, let's just see if the same proof works. Why did that not work? Ooh. Okay, we have to do something else. So let's do simp xdiff again, because it seems like the way to start. And now we've got two goals. Okay, I see, okay. So let's split. And now the first goal might be solvable by simp. Let's try this. If I do simp, how far do we get? Not very far. That's a shame. I want to do 2.re. How do I... This is a bit annoying. Show rez plus rez equals 2 times rez, right? It suffices to prove. I claim it's a... Oh, there we go. So now maybe the simplifier will do that. It doesn't do that. Okay. Oh, ring will do it. Right. Did ring do it before? No, ring didn't do it before. So there we go. And now what's going on here? I seem to have to prove two. I either have to prove that the imaginary part of 2 is 0, or the real part of z is 0. I'm going to go for the imaginary part of 2 is 0. There. And the simplifier should do that. No! The imaginary part of 2. What? Oh, let's try this. Oh, that's worked. I'm quite surprised that... Well, there we go. That was harder than I thought. God, this game's obviously worth something. Conjcon z is z by xdiff by xsimp should do that one. This one here by simp, maybe. That has not worked. Let's see what happens. Oh, fair enough. Well, let's try simp xdiff then. That's worked. And this one, I'll try the same again. Simp xdiff. Yeah, I have no interest in proving these goals because they're mathematically trivial, right? So we should be able to get automation to kill them. I see, I see. So the thing that's doing all of these is this, isn't it? By simp xdiff. So most goals, most goals are by simp xdiff. That one wasn't. Was that one? No, that was harder. But all of these up here. Yeah, fair enough. That's a by simp xdiff. Yeah, instead of by xsimp, I can do by simp xdiff. Right, let's finish it. So we've accidentally proved that complex conjugation is a ring homomorphism. Because to prove that it's a ring homomorphism, we need to prove it sends 0 to 0, it sends 1 to 1, and it preserves addition and multiplication. And we've done all those lemmas up there. There you go, there's the fact that it preserves multiplication. So that's done, and now finally, just two goofy things. How do we know that simp is an involution? How do we know, sorry, how do we know that conj is an involution? What does that even mean? Unfold involutive. Okay, so we have to prove that for every complex number, its conjugate of its conjugate is x. So we can intro z And now we've proved this already. This says, this is computer science notation for show conj of z equals z, right? That's what we're trying to prove. And we just proved that, right? That was this. And there you go. That's tagged as a simp lemma. So in fact, simp should do this. It did. So there we go. We proved that complex conjugation is involutive, which means if you do it twice, you get it. So that can probably go, actually. So there we go. And finally, we've got to prove it's bijective. And that should follow from the fact that it's involutive, right? Let's go and see. Here's the definition of involutive. There we go. So here I'm in MathLib. Here's the definition of involutive in MathLib. And as you can see, just like what we're doing, after a definition, you then prove a whole bunch of lemmas. About that definition. And one of the lemmas it's proved is involutive dot bijective. So it seems to me that we can prove this by exact involutive dot bijective, and we can't. And why have I? Oh, involutive bijective. Oh, I see. And then we want. Oh, we should apply it, of course. Apply involutive bijective. And so now instead of having to prove it's bijective, we just have to prove it's involutive, and that's now exact conj involutive. So there we go. Sorry I'm slightly over time, but that's the end of that. I've done levels 1 to 3. So next week I'll do level 4, which is the proof that the complex numbers are a field, and then I'll have a look at level 5, and then who knows what I'll do. So there we go. So next week level 4 and level 5, and I'm done. So I'm now going to Discord. I'll send you the Discord link. I'm now going to spend a few hours at Discord, where we're just going to goof around and do dumb stuff. I mean, we're going to do some speed running. We're going to try speed running the tutorial project. Here's the Discord link for anyone who's interested. And I'm out of here. Thank you very much.